Good afternoon, everyone. My name is Sanjana Rane, and for the past few years, I have been studying the effects of the environmental pollutant acrolein on renal fibrosis. I first became interested in this project after discovering a study sponsored by USA Today called the smokestack effect. This study aimed to test the air surrounding our nation's schools, testing for exposure to cancer-causing toxins and other toxic chemicals. So, out of curiosity, I plugged in my school name, only to discover that we are in the 2nd percentile nationwide. This was incredibly alarming and inspired me to research air pollutants, eventually focusing on acrolein. Acrolein is an EPA-labeled air toxin that is produced in the environment through a variety of means, including industry fumes, especially the petrochemical industry, and cigarette smoke, both of which are highly prevalent in my state of Kentucky. And although acrolein is known to modify DNA and proteins, there is currently no industrial cap on the amount of acrolein that's allowed to be released into the environment. This was troubling and made me wonder how exactly acrolein is affecting our bodies, but more specifically, how exactly acrolein is affecting our kidneys, given that one of the main roles of our kidneys is to filter out toxins from our blood. And in general, after sustaining kidney damage, an unsuccessful healing process in our kidney tissue leads to renal fibrosis. This causes a decline in renal function and ultimately ends up becoming end-stage renal disease, or ESRD, which is the complete and irreversible failure of our kidneys. There are 4 overlapping phases of renal fibrosis, but in general, there are 2 main aspects that needs to be considered. The first is the fibrotic aspect that stems from an accumulation of extracellular matrix proteins that leads to a buildup of scarring tissue that inhibits function. The second, and often overlooked aspect, is the inflammatory aspect. Proteins called DAMPs, or damage-associated molecular patterns, recruit excess numbers of inflammatory cells that exacerbate injury. The purpose of my project was first to clarify acrolein's damaging effects on renal cells, and second, see if I can identify a therapeutic target that can help treat acrolein-induced renal disease. Studying renal fibrosis and ESRD is incredibly important because right now the 2 main methods for treating renal disease is dialysis, which is very long-term and incredibly painful, or kidney transplantation, which carries its own set of risks. Not to mention that close to 80% of the people on the transplant waiting list are waiting for a kidney. Moreover, treating ESRD has cost the United States government over $87 billion as of 2012. So identifying a new target can lead to the generation of new therapies that not only can potentially save lives, but can also help reduce this financial burden. While investigating how I was going to approach this topic, I came across the protein NFE2, or nuclear factor erythroid-derived protein 2. This protein was identified as an HSP27, or heat shock protein 27 binding protein in neutrophils. But I wondered whether NFE2 could also play a role in renal cells, given that HSP27 has been linked to renal fibrosis in the past. For my project, I hypothesized that acrolein expression would regulate renal fibrosis by modulating the expression of NFE2, a possible DAMP, as well as the pro-fibrotic protein CTGF, or connective tissue growth factor. For my first experiment, I exposed renal cells, or HK11 cells, to varying doses of acrolein for 24 hours, and then I immunoblotted cells for cleaved caspase-3, a known marker of apoptosis or programmed cell death. And I saw that at the 50 micromolar acrolein concentration, there was a significant increase in caspase-3 cleavage, suggesting apoptosis. But to corroborate these results, I also treated cells with acrolein and stained them with hex dye, which binds to DNA in the nucleus. And as you can see from these images, cells exposed to larger concentrations of acrolein exhibit condensed nuclei, a characteristic of apoptotic cells, confirming acrolein's role in renal cell apoptosis. For my next experiment, after treating cells with acrolein, I immunoblotted them for the pro-fibrotic protein CTGF as well as NFE2. And I saw that acrolein expression was significantly increasing the amount of CTGF expression as compared to control cells, suggesting acrolein's role in fibrosis. However, I also saw that acrolein was significantly reducing the amount of NFE2 expression. Now, this was interesting to me, and I wondered whether, since it's suppressing NFE2 within the cell, is it maybe expressing it outside the cell. To test for this, I collected the cell supernatants, which is the cell culture medium, and immunoblotted those for NFE2. And I saw that cells exposed to greater concentrations of acrolein exhibited a significantly higher amount of extracellular NFE2. Now, this is really interesting because it means that acrolein is modulating the expression of NFE2 differently inside the cell versus outside the cell. I first decided to tackle the problem of inside the cell. I decided to overexpress NFE2 inside the cell using a Pius vector, treat those cells with acrolein, and then immunoblot for CTGF once again. And I saw that by the overexpression of NFE2, it significantly decreased the amount of acrolein-induced CTGF expression, as well as it decreased the amount of acrolein-induced caspase-3 cleavage. So just a quick summary, I'm showing that acrolein exposure is increasing the profibrotic CTGF expression as well as renal cell apoptosis. And it's decreasing intracellular NFE2 while increasing extracellular NFE2. And I also showed that the overexpression of intracellular NFE2 is inhibiting CTGF, suggesting its role in fibrosis. Yet the role of this extracellular NFE2 component still remained unknown, and that's what I decided to tackle in the next phase of my project. I wondered if maybe this extracellular NFE2 was acting as a pro-inflammatory damp. So to test for this, I exposed renal cells to varying doses of acrolein for 24 hours, and I collected the cell supernatants, which contains that extracellular NFE2 component that I want to study. I then took human neutrophils and exposed them to my NFE2 supernatants, looking for activation through a variety of assays. I first examined MAP kinases, or mitogen-activated protein kinases. These are a series of 3 kinase cascades whose terminal ends are ERK, P38, and JNK. ERK pathways are mainly shown to be pro-survival, whereas P38 and JNK pathways are mainly shown to be pro-apoptotic or pro-death. So after exposing my neutrophils to these supernatants, I immunoblotted them for a variety of proteins and saw that there was a significant increase in the pro-survival phosphorylation of ERK, no change in the pro-death phosphorylation of P38, and a significant decrease in the pro-apoptotic marker cleaved caspase 3. But before I could confirm these results, I realized that I could not definitively say that these results are due to the extracellular NFE2 component. So to adjust for this, I decided to remove NFE2 from my supernatants and repeat this experiment again by using immunodepletion, which I used using an NFE2 antibody, as well as proteinase F-rose beads, which creates an insoluble complex. So I exposed neutrophils to these NFE2 deficient supernatants and repeated the experiment again, and this time I saw that there's now no change in the pro-survival phosphorylation of ERK. There's a significant increase in the pro-death phosphorylation of P38, and there's a significant increase in pro-apoptotic cleaved caspase 3. So with NFE2, I'm seeing prolonged neutrophil survival, and without NFE2, I'm seeing neutrophil apoptosis. But I decided to take it one step further and examine actin polymerization. Actin is a cell structure protein. When a neutrophil becomes activated, actin will polymerize, modifying the shape of the cell, helping it move throughout the body. I've treated cells with acrolein, fixed, permeabilized them, and stained them with rhodamine fluoride dye, and viewed them under a confocal microscope. Note the diffuse staining and round circular shape of the control cells. Now, if you look in the bottom right corner, notice how all the actin is moved toward one side of the cell. That's as if to propel the cell forward throughout the body. Also, look in the top right corner, and you can see how elongated the cell shape has become in comparison to these round circular control cells. This shows that my supernatants are stimulating actin polymerization. I even examined whether my neutrophils would chemotax or move in the direction of these NFE2 supernatants. To test for this, I used a 2-chamber assay. I put my neutrophils in the top chamber, and I put my NFE2-containing supernatants in the bottom chamber, or I placed FMLP in the bottom chamber, my positive control for neutrophil chemotaxis. And I saw that, similar to FMLP, these supernatants demonstrated a significant increase in the amount of neutrophil chemotaxis. But to definitively confirm extracellular NFE2's role as a damp, I repeated the same set of experiments using recombinant NFE2 as well, and saw that, once again, there was an increase in the pro-survival phosphorylation of ERK. There was actin polymerization in comparison to control cells. There was also a significant increase in the amount of neutrophil chemotaxis, similar to the level of FMLP. I even demonstrated that neutrophils that had been exposed to recombinant NFE2 had a significantly higher percentage of viable cells as compared to control cells, similar to the level of LPS, my positive control for neutrophil survival. So my results supported my hypothesis because they're showing that acrolein exposure is increasing CTGF within the cell, causing fibrosis, while decreasing NFE2 within the cell. It's also increasing the amount of extracellular NFE2, which is causing inflammation. This allows me to conclude that intracellular NFE2 is acting in a way that regulates acrolein-induced renal fibrosis, but extracellular NFE2 is acting as a pro-inflammatory damp. So why is this important? Well, first off, NFE2 has great potential to be a therapeutic target in renal disease because it controls both aspects, fibrosis as well as inflammation. But this also applies to cancer patients. The popular chemotherapeutic drugs, cisplatin as well as cyclophosphamide, are highly potent at killing cancer cells. However, they are shown to be highly nephrotoxic. And actually, acrolein is a metabolite of both of these drugs, and studies have shown that they are highly prevalent in kidneys and urine of patients who are receiving both of these drugs. Therefore, an approach targeting NFE2 could potentially help people who receive drugs such as cisplatin and cyclophosphamide. So my proposed two-pronged approach goes as follows. My first prong would address fibrosis by overexpressing NFE2 within the cell, which would cause CTGF expression to go down, thus blocking fibrosis. But the second prong would address this extracellular NFE2 component. Through antibody therapy, I would block extracellular NFE2 activation. This would reduce inflammation by upregulating neutrophil apoptosis. So this treatment stands to be incredibly beneficial by helping save millions of lives. And this is incredibly important because I'd like to leave you with something to think about. Every day in the United States, close to 12 people die while waiting for a kidney transplant. So investing time and energy in finding new therapies can hopefully save thousands, if not millions of lives. Before I conclude, I'd like to thank the Siemens Foundation, Discovery Education, and definitely the George Washington University for giving me the opportunity to present my research here today. I'd like to thank the judges as well as my fellow competitors. I'd like to thank Dr. Shunying Jin and Ms. Terry Manning at the University of Louisville for their time, Mr. Glenn Zwanzig, my science teacher, as well as my school, DuPont Manual High School, and my parents for all of their support. Thank you very much.